Okay, we'll start this video here. So we're in section 11.3 talking about the integral test. We're on this theorem called the P-series test. And the P-series test is going to be really important. You'll see that a lot in, for various things in chapter 11. And it says that the sum going from n equals 1 to infinity of 1 over n to the p converges if p is a number that's bigger than 1, and it diverges if p is a number that is bigger than 0 but less than or equal to 1. Okay? So if we look at a quick proof of this, if p is 1, then you have the integral going from 1 to infinity of 1 over x to the p dx. P is 1. Okay, so that's the limit as t approaches infinity of the integral going from 1 to t of 1 divided by x dx. And that's equal to the limit as t approaches infinity of the ln of the absolute value of x going from 1 to t. Plug in the bounds, the ln of 1 is 0. So we got the limit as t approaches infinity of the ln of the absolute value of t, which is going to be infinity. So t is approaching infinity, so the ln of t would be also approaching infinity. By the way, if p is 1, we have a harmonic series. We looked at that in section 11 too. The harmonic series is a divergent series. That's a really important series that you'll see all over the place in chapter 11 also. Okay, the harmonic series could be called a p series though when p is 1. So now, okay, what if p is a positive number but p is not equal to 1? Then the integral going from 1 to infinity of 1 over x to the p dx, that is equal to the limit as t approaches infinity of the integral going from 1 to t of x to the negative p dx. And using the add 1 to the power divided by the new power rule, we got the limit as t approaches infinity of x to the 1 minus p divided by 1 minus p. And we're going from 1 to t. 1 divided by 1 minus p, that's a constant that can come outside of the limit actually. Because anything involving t has to stay inside the limit, of course. So then if I plug in the bounds, I got t to the 1 minus p minus 1 to any power is always 1. Okay? And let's see. So if t is excuse me, if p is a number that is bigger than 1, so like suppose that p is 2, okay, then I have the limit as t approaches infinity of t to the negative first part of the sum is 1 over t minus 1. The limit as t approaches infinity of 1 over t, that's 0. Okay, and so I'd have negative 1 divided by 1 minus p. And in general, I'll always have that if p is a number that's bigger than 1. If p is a number that's bigger than 0 but less than 1, like suppose that p is 1/2, t to the 1 minus 1/2, that's t to the 1/2, or the square root of t. And as t is approaching infinity, the square root of t would also be approaching infinity. And I'm subtracting 1 dividing by 1 minus p, so what? I'm still going to be approaching infinity. Okay? So in general, if p is a number that is bigger than 0 and less than 1, you're going to be approaching infinity. Okay, so you'd have a divergent series if the p-value is a number between 0 and 1, including 1. Okay, so for example, suppose that I have the summation as n equals 1 to infinity of 1 over n squared. Well, I can know that that converges, right, because the p-value would be 2. And from what I said up here, okay, anytime the p-value is bigger than 1, you got a conversion p-series. Okay. In this second one, so I got the summation as n equals 1 to infinity of 1 over n. That's the harmonic series, which we don't know diverges, but it's also a p-series where p is equal to 1. Okay, and that diverges also. And suppose that we got the summation as n equals 1 to infinity of 1 over the square root of n. Okay, well that would be a divergent p-series also because p is 1/2, right? And if p is a number that's between 0 and 1, you're going to get infinity there. Okay, so if I add up all infinitely many of these terms, 1 plus 1 over root 2 plus 1 over root 3 plus 1 over root 4, right, the grand total would be infinity. Okay. Let's take a look at, I got one more example in this section. So in this one, we're going to use the integral test if it applies. So sometimes these don't apply. You don't just want to blindly set up some integral and start computing it, okay? Especially if the test doesn't apply. And there's 3 conditions that have to happen in order for you to use the integral test. You got to have a positive function. It's got to be continuous, and it's got to be decreasing on the interval 1 to infinity. Or eventually, the terms have to decrease. I'll talk about that a little bit more here in this example. But we're going to find the summation as n equals 2 to infinity of 1 over n times the ln of n squared. Okay, so we have a positive function if n is some number that's 2 or more, 1 over n times the ln of n squared, that's always going to be positive. And you're going to be continuous everywhere on the interval 2 to infinity. The only numbers that make this a problem is when n is 0 and when n is 1, the ln of 1 is 0, right? That's by the way, that's why we're starting at 2 and not 1, because you can't use 1, right? Because you can't divide by 0, okay? So the only thing left to do then is to show that the terms decrease on the interval 2 to infinity. Okay, I'm going to use the increasing and decreasing test, going back to Calc 1 here. And if f of x is 1 over x times the ln of x squared, then the derivative, bottom times the derivative top is 0, minus the top times the derivative of the bottom. That'd be a product rule, and within the product rule, you're going to use the chain rule. So you got the first times the derivative of the second, that's 2 ln x times the derivative of the ln of x, that's 1 over x. And then plus the second, ln of x squared, times the derivative of the first is 1. Again, this is all over the denominator squared. Okay, so then let me go ahead and simplify this here. The x's will cancel. And if I factor out an ln of x out of the top, then I'll have negative ln of x times the left over here would be 2 plus the ln of x. Okay, and you're dividing by x times the ln of x squared. Okay, so well, that's going to be less than 0 whenever x is a number that is bigger than 1 or greater than or equal to 2. Okay, because since we have a sum here, we're only using counting numbers. But the denominator will always be a positive no matter what for when n is or when x is 2 or more, and the ln of 2 or more is always going to be a positive, right? So this guy's always going to be positive. This guy's always going to be a positive. I got a negative in front. So there's a negative divided by some positive number. Okay, that's going to be less than 0 anytime that x is greater than or equal to 2. So that means that you're going to be decreasing on the interval 2 to infinity. Okay, so in other words, we can use the integral test. The test applies. Now, again, when we use the integral test, it's not necessary to start the series or the integral at n equals 1. So, for a lot of these problems, you're going to be starting the series at 1. It doesn't have to be that way, though. Okay, just wherever you start, and then with this third condition here, where you're checking to see if the terms are decreasing. So all we care about with that is that they eventually do decrease. It's okay if at the beginning the terms don't decrease, but eventually they do decrease forevermore, if that makes sense. Okay. So anyway, these terms are going to be always decreasing on the interval 2 to infinity. But so if we set up the integral test, we got the integral going from 2 to infinity of 1 over x times the ln of x squared dx. And that would involve a u substitution. So if u is the ln of x, du is 1 over x dx. And so then I'm going to be integrating 1 over u squared du. Now remember, I got to change the bounds whenever I have an improper integral here. Okay, and I've used the u substitution. So if x is 2, u would be the ln of 2. And if x is infinity, the ln of infinity, something growing without a bound, is going to be infinity. I guess you could have the ln of t up top. That'd be fine. But I'm just going to have t up top. Okay, because if t is growing without a bound, then the ln of t is going to be also growing without a bound. Okay, so you got the limit as t approaches infinity of the integral going from the ln of 2 to t of u to the negative second power du. And so that would be the limit as t approaches infinity of negative 1 over u, and you're evaluating this from the ln of 2 to t. So then when I plug in my bounds here, I got the limit as t approaches infinity of negative 1 over t, and then minus a negative means plus 1 over the ln of 2. Okay, now t is approaching infinity. So 1 over t, that's me going to 0, right? Because the denominator is me growing without a bound as the numerator just sits at 1. Limit of a constant is always a constant. So you get 1 divided by the ln of 2. Okay, well, that's a finite number. So that tells me that this integral is going to be convergent. And if the integral converges, then the series also converges. Okay? And remember, now just because the series converges, that does not mean that I'm going to get 1 over the ln of 2 as the answer. And in fact, I have no idea what the answer is. Just that the series converges. Okay, which is all we need to know for problems, for a lot of the problems here in chapter 11. Really from this point on, all we care about is that does the series converge or diverge? Okay. All right. So that's it with section 11.3. Have a go at the homework there, and in the next video we'll start in on 11.4.